All right. So good morning again, everyone, and good evening to you, Haoliang. Thank you very much for joining us. Hi. So Haoliang, we're really pleased to have you as part of this workshop. And Haoliang is going to talk to us about generalized and explainable AI system for real-world challenges. Just a brief introduction. Haoliang is an assistant professor at the Department of Electrical Engineering at the City University of Hong Kong. Sometimes people confuse that with CUHK, which is Chinese University of Hong Kong. They're both great institutions. Haoliang earned his PhD degree from NTU, Singapore, and his current research primarily focuses on secure face recognition, fake news detection, multimedia content forgery detection, transfer learning, that includes domain generalization and domain adaptation, and their practical applications. So quite wide-ranging focus, and we're really looking forward to your talk. Over to you, Haoliang.
Thank you very much for introduction. Hello, everyone. My name is Haoliang Li. I'm currently working at the Department of Electrical Engineering, City University of Hong Kong. So I'm quite happy to share with you my recent research about the topics of generalized and explainable AI. So the topic of my talk is generalized and explainable AI system for real-world challenges. So one of my research interests is based on the machine learning. Mainly focus on the application of computer vision and other kinds of image processing algorithms. So here maybe I want to give a brief overview of the research on the image processing and also the computer vision. So which is about how can we represent an image. So we know that the computer vision has been analyzed for many decades, right? So in the past, our researchers maybe focus on these statistical features or handcrafted features, right? So for example, given an image, so we want to explore the edges, lines, or contours information, right, by extracting features. And then we further want to utilize the features for many downstream tasks. But nowadays we have deep learning, right? So starting from 2012, so we have the convolutional neural nets, and now we have this transformer-based model, right? So even based on the ImageNet competition, right? So deep learning models can already surpass our human beings, maybe around like 2017, right? So nowadays, right, deep learning becomes more powerful, and besides directly utilizing the deep learning models for many different kinds of computer vision tasks, including medical image analysis, right? And one can also utilize the learn feature or the hidden feature extract by our deep neural net, right? For many other kinds of applications. So since we can already achieve a very desired performance, right? So by utilizing deep learning for computer vision, so we want to ask a question whether we can already solve the computer vision problem. The answer is actually no, right? So one reason is that models do not generalize well to new domains, not like our human, right? Even now we have this foundation model, right? But still, right, when you are using the ChatGPT, right? So we always have this, so you can find the words, right? Based on the website of the GPT that the model, right? So the learning information is only before like 2021 or 2022, right? Something, right? Which cannot be generalized, right? Maybe to the, maybe we call this as extrapolation, right? Not like our human beings. And then maybe you may always wonder, right? So since deep learning models, right, are powered by the big data, right? So why not we just collect the big data, right? So even for some new computer vision tasks, right? So we can always collect sufficient data, and then we fine tune the model. But the answer is that the big data are not always available, right? So one reason is that it's impossible to consider data based on all scenarios, right? Because for computer vision problem, we have to consider these the capturing devices, right? And we also have to consider the diverse environment, right? So which is impossible, yeah, to consider that data collected from all possible conditions. And also on the other hand, right, so data can be protected under the privacy regulation. So I think this issue becomes very important, right, in terms of the healthcare, the medical image analysis, right? So where we have this the privacy regulations. So therefore, the idea of domain generalization, right? So we want to build a system, yeah, for the machine learning task, right, in the previous unseen data set, right? So given one or multiple training data set, right? So the idea for domain generalization is that, right? So we want the real-time deployment, right? Because unlike the problem of domain adaptation, right? We have the unlabeled target domain available, right? And then we can utilize maybe the labeled source domain data as well as the unlabeled target domain data, right? And then we can tune the model by using domain adaptation. But for domain generalization, right? Unfortunately, the testing data are not available, right? So either because we want to have the real-time deployment purpose, or the data, the test data could be protected under the privacy regulation. So I believe that other speakers, right? So you already learn or hear a lot, right, from other speakers about the ideas of domain generalization, about this the basic concept, as well as some other advanced algorithms, yeah, which is related to domain generalization. So here, maybe I just want to briefly summarize what we have done so far, right? So yeah. So we start to work on this problem, I think, since 2017, and we focus on both the algorithm level as well as the application level, right? So as you can see, yeah, we also explore the medical image analysis, by utilizing the idea of domain generalization. Yeah, as for the algorithm level, so we explore quite different machine learning algorithms, like including the domain alignment, as well as feature disentanglement, knowledge distillation, and also we want to explore whether we can do some data processing by using the Fourier transform. Yeah, and besides the image task, right, we also explore the video, right? So because we are dealing with video every day, right? So from a lot of social media platforms, so it's highly likely that the videos, right, in the real world can be corrupted, by different kinds of noises, right? Can because of the compression, can because of the lossy wireless network, right? And also can be due to the capturing, right? So of capturing devices. So that's why we have this sharp noise. We also have a lot of blur, and we also consider different weather condition like fog, right? And also the rain. And besides, we also consider the artifact of the video compression, including like H.265, and we also consider bit error and the packet loss level, right? So which is due to the lossy wireless network. So we analyze the robustness, of the video classification under this scenario, right? Yeah. So another thing I want to share with you is what we call as involving domain generalization. So which we think is it's a promising new research direction. Yeah, maybe it can benefit some healthcare application. Right. So one possible application is for the disease diagnosis. Right. So for example, maybe we have the data, right? Yeah, for a particular person, maybe when he was young and also at the middle age, but we also want to predict whether there are any risk, right? So he or she will have any potential disease, like that. So in this case, we have this involving domain, right? Although we analyze the same person, but because of the condition of the person can be changing, right? So we call that the domain is involving, like that. So we also propose an algorithm based on this variational inference, right, to model these involving patterns, through an LSTM model, right, to capture this involving pattern, which can help us to generalize better under different kinds of benchmark data set. Yeah, so I want to summarize what we have done, so far. So maybe the main idea for this talk is that I want to give you something to introduce something different about this domain generalization. So we know that the popularity of the deep learning, right, not only attract the researchers and also engineers, in the community of AI, but also the people from the community, in other related area, for example, software, right? So maybe the people in the area of AI, right? So we want to apply the mathematical model or signal processing model to try to understand the generalization or the robustness of the deep neural network. And also, meanwhile, the people in the field of software engineering, right? So they try to explore, right, to analyze the behavior of the deep learning model, from the perspective of the software engineering. Right. So for the traditional software deployment, right? So as you can see from this figure, right? So how the software people analyze the problem, is that we have the input and output, right? And we want to analyze the decision logic, where the decision logic is actually made by the developer, right? So for example, through coding or some other kinds of platform. So how about the machine learning system, right? So in this paper, right, so they want to make a comparison, right, of the machine learning model as well as the software model, right? So for machine learning model, we also have a similar uh, flow, right? Just like a software deployment, we also have the input and the output, right? So here the input and output could be the data, the training data, as well as the corresponding ground truth, right? And then the decision logic is actually done by the algorithm development, right? So we have the training data, we can do the feature selection, but now we have the deep learning model, right? And then further, we can have the algorithm tuning, right? So now we have the decision logic. So maybe at a high level, right, the development of the software as well as the machine learning system could be similar, right? So in the field of software engineering, right, so we have the term we call the software quality assurance, right, to make sure that we have a software maybe developed by writing the code, right? So we want to make sure that the software, the quality of the software is high, right? So how do we do this? So in the community of software engineering, right, so we have the term we call the code coverage. So maybe I want to give you a motivated example, right? So for example, when we write a code, right? So we always have many branches. The branches could be defined by using the if-else, right? The if-else structure, right? So if this condition is satisfied, we go to this branch. Otherwise, we go to the other branch like that, right? And in the code, we may have a lot of if-else structure like that, right? So you can imagine that if during the testing, right? So after we finish writing the code, we have to test the code, right? To test the code, we have to generate a lot of input, right? A lot of samples. And then we have to get the corresponding output, right? Then if we can get the right output without error, right? So we can say that the code, the quality of our software is maybe okay, right? But you can imagine that if our samples for testing, okay, given a branch, all the samples actually activate only one branch. So for example, here, we only have the no branch, right? We only activate the no branch, where is no bug exists, right? So then you may think of this, okay, everything works well, no bug. But during the deployment stage, we have a new sample. We call this as OOD, maybe the out of distribution sample. This sample actually generated yes branch. Then we have the buggy code, which trigger the buggy code. Then we have the problem, right? So the idea of code coverage analysis is that try to generate the diverse samples which can maximize the code coverage. In other words, we want the samples to go through both the no branch as well as the yes branch for all possible structures, code structures like that, right? So so based on this idea of the code coverage, we have a lot of metrics yeah, based on the data flow analysis and based on the control flow analysis. So the key idea, yeah, for the software quality assurance is to make sure all the branches can be activated during the testing stage. Okay, so now we want to borrow the idea, right? Because we want to have some, some comparison, between the traditional software deployment and also the machine learning system development, right? So how we can analyze a machine learning model, right, from the perspective of software engineering. So in this paper, right, so the author proposed a very novel idea called the deep neural net quality assurance, by proposing a new metric called the neuron coverage, right? So similar to the code coverage. So in the neuron coverage, we have a lot of neurons, right? And then after we train the model, right, and then we want to do the testing. So we want to evaluate, right, whether the neuron has been activated or not, right? So the idea is that if neuron has not been activated during the training stage, but has been activated, during the testing, we may have some bug. Right. So in this paper, the author proposed a very novel metric called the neuron coverage. So after we training the neural network, and then we want to do the testing, right? So to do the testing, we may have some testing samples which activate the neurons that has not been activated during the training stage, right? So these kind of samples, the inputs may be treated as the auto distribution samples, right? And then to further improve the robustness of the deep neural networks, we further utilize these samples, right, to train the network again, to improve, right, the robustness of the neural networks, or we can say this to improve the quality of the neural networks. Okay, so based on this string, right, so there are still some other kinds of neuron coverage proposed, right? So for example, this deep gauge, deep test, and deep hunter. So the key idea by proposing these metrics is to define, right, how we can tell a neuron has been activated or not. So in the original paper, right, so the author proposed a threshold, right? If the value, the output of the neuron is larger than the threshold, we can call that the neuron has been activated. Otherwise, the neuron has not been activated. Okay, so here the idea, right? So is the neuron coverage is actually introduced during the testing, right? During the testing stage. Yeah, but for the problem of domain generalization, we actually, what do we want is for the real-time deployment, right? So maybe we want to, just to make our deep neural networks to be generalized as much as possible, right? So what do? Is that we want to introduce the idea of neuron coverage to the problem of the domain generalization. So let's recall that the existing techniques for domain generalization are all based on the machine learning algorithms, right? Like the distribution alignment, meta-learning, contrastive learning, adversarial training, right? So in our works, which is accepted by our paper, right? So we want to introduce a new perspectives. So we're not going to say that our proposed method works better compared with the existing machine learning-based algorithm, but to look at the problem of domain generalization from another perspective. So which is that we want to treat the deep neural network as a software system. Okay, right, like that. Okay, so now what we want to propose here is the neuron coverage guided training, right? So I recall that for the neuron coverage, right? The original idea for neuron coverage is for deep neural network testing stage, right? But what we want to do is to apply the neuron coverage during the training stage, like that. So we want to redefine the activation of the new activation, right? So here is our definition. A neuron is inactive during the whole training process. Once it gets activated during the evaluation, errors may happen. So that's the original idea of the neuron coverage, right? So for the problem of the domain generalization, so we can also imagine like this, right? During the training stage, there might be some neurons which has never been activated by one single input, right? But during the testing, once we have the out of distribution data, we can activate that neurons, right? And then error happen, right? So this is what we call it as the, maybe similar to the bugs in the software engineering. So the key idea is that, we want to apply the data flow in software and the code statement coverage to the data flow in the DNN neuron coverage. So here's what do we do, right? So we want to apply the concept of the activating neuron, right? So we define based on the normalized output value, right? Because for different kinds of tasks, right? Maybe the output, right? The magnitude of the output, could be different. So we use the normalized output value, and then we have the predefined parameter t, which is used at the threshold. So here is a pipeline, right? So based on a single epoch, right? So when a new epoch starts, right? So at the very beginning, all neuron activation status as false, right? And for each iteration, we keep track of the inactive neurons, right? And then we update the output, right? Based on the coverage loss term. The coverage loss term is defined like this, which is basically to examine, right, the normalized output value. Like that. So what do we want to do is try to maximize the coverage loss, right, during the next iteration. So unlike by using the neuron coverage only for the DNN testing, so we want to incorporate this coverage, neuron coverage as a loss function, right, during the training. So this is our loss, right? So because we want to maximize this term, right? So together with the task loss, right? Maybe as a cross entropy, right? So here is a final coverage loss, which is just a combination of the maybe cross entropy loss together with the magnitude, but the normalized magnitude of the output of the neurons, like that. Okay. So so now we can successfully, right? So to transfer the idea, right, by using the neural ideas during the deep neural nets testing to the deep neural nets training, like that, right? But the training process can be very complicated, right? Which is very unlike the traditional software deployment. Because for the training, right, by only examining the neural activation, right, we only examine the binary information of a certain layer. There's no layer interaction like that, right? Because for a deep neural net, information are actually, right, transfer from the very shallow layer to the very deep layer, like that. So what we want to do here is to apply the idea of the control flow in a software branch and conditions to the control flow in a deep neural net by using neural gradients. So what do we do here is to consider two samples, right? Maybe the original samples as well as the augmented samples. So our assumption is as long as they have the same semantics, they should have the similar control flow. So which leads to the similar loss term based on the gradient. So although our motivation is coming from the control flow, right? But we found out that this loss term is actually similar, right, to the other loss, right, like the fish, right, which appears in ICML paper. They also analyze the gradient similarity, right? So our loss is similar, to the fish, method at a high level. But our final loss, then we have this the coverage loss for the original sample as well as for the augmented sample, as well as the similarity loss, between these two samples, like that. Okay, so because of time limit, so maybe I just want to share with you some results. So we have tested on both the object classification as well as the segmentation. So we show that some desired performance have been achieved, right? And we also analyze on the multiple source domain generalization tests. We also found that some good performance has been achieved. Okay, so one interesting thing is that, we want to analyze, right? So the behavior of the neurons. So why the inactive neurons during the training stage, but has been activated during the testing, can lead to this wrong behavior, right? So we analyze one neurons, right, from the ResNet 18. The details can be found in our papers, right? So by applying the baseline method, right, so we found that the input which can generate the wrong classification, right? So you can see that the activated information actually capture no semantic information, right? capture no semantic information. But by using our laws, right? So by using our method, right, we can capture useful information. For example, here the active region is all based on the eye areas, right? So which may be helpful, for the person classification task. So this is very interesting because we can link the idea of software coverage together with the AI expandability. And by the way, right, so our visualization tool is to the by using the network dissection, where the code and the details can be found in the paper below. Okay, so because we touched the explanation, right? So maybe I want to introduce more about this. So the existing many existing methods for explanations are based on the attention, right? So attention weights can be always non-negative, right? Based on this equation. But we want to ask a question is that whether the positive attention weights indicate that the feature contributes to model prediction, right? So this kind of attention, right? So we always want to have the values which are maybe high, some large values, right? Which maybe indicate some important areas, but which may not be true. So here are some examples. Maybe I just want to show you this one. So maybe based on the VQA task, right? So what is skill eating? So the original sample, right? So we have this, as the maybe the donut, right? Like that. But as long as we want to put masking on part of the donut, right? And then we can see that the explanation based on attention can lead to error, right? So if no mask, right, so we can see that the highlight region are perfect, but once we put a partial mask, the attention model can be wrong, like that. So which means that there are some limitations of existing methods based on explanation, right? So the existing methods are based on the importance correlation by examining the magnitude of the attention weight, right? So, but we want to argue that the polarity, right, is also important. It's that the sign is also important, which has been largely, ignored in the previous method. So what do we do is that we want to propose a faithfulness violation test. So the idea is to measure the ratio of the test samples violating polarity consistency, right? So here is the algorithm, right? So we just want to analyze, right? Maybe whether the most influential feature, right? Maybe can be found by using one explanation method, but then we further remove this feature, and then we check the final prediction, right? The confidence of the final prediction. And then the violation could be found if this term, right, is satisfied. So in other words, by removing the most influential features can lead to the increase of the prediction scores, like that, right? Okay, so the idea is quite simple. And then to examine the so why we want to introduce this faithfulness test, we analyze 3 questions: why we need a faithfulness violation test, and how existing method perform on faithfulness, and what factors dominate the faithfulness violation issue. So regarding the first one, right, so why do we need the faithfulness violation test? Actually, there already exists some faithfulness matrix, right? But why do we need to introduce another violation algorithm? So here I want to show you one example by using the VQA data set, right? And then we consider the existing methods for the faithfulness analysis, the sufficiency, and another one is CUHK, which are all designed for the faithfulness evaluation. But as you can see, based on our own violation, right? So the violation score can be very diverse, ranging from 0 to 1. But there is no difference, right, for the sufficiency as well as this CUHK, right? So which means that our violation matrix actually introduced, right, maybe something new, right, where the sufficiency matrix as well as the CUHK cannot cover. And then we want to analyze the importance, right, of our faithfulness test, right, to the explanation method. right? So if the existing evaluation method can truthfully reflect the faceness, so we will observe that the scores, right, of the explanation, there might be proportional, right, yeah, to our faceness score and the existing explanation method. But unfortunately, we do not see such pattern, right? So for example, yeah, for this one, right, maybe some scores for explanations are very high, yeah, but for our violation can be very low, right? So which is a contradict, right? So which shows that the existing explanation methods, right, cannot suffer from the faithfulness violation issue regarding the polarity consistency. And last but not the least, we want to study, right, the dominant factors. What kind of factors influence the faithfulness, right? So we want to analyze, to do some based on the result, right? So we see that the capability to identify the polarity and also the complexity of the model architecture. So we identify that there are two issues, right? So one is the gradient, right? And the explanation, the attention scores, as well as the corresponding gradient. Yeah, both of them plays a very important roles for the faithfulness analysis.
Sorry,
Okay.
Haoliang.
Yeah, so I think that's all about my my talk. So I introduced two kinds of algorithms based on the domain generalization as well as the explanation issue. And also I want to discuss some possible future direction, right? So yeah, one is the generalization issue, right? To see whether or how and why the model could be generalized. And also is beyond the generalization, right? Can be trustworthiness issue of AI as well as the fairness issue of AI. And last but not the least, right? So I think one important thing, especially for healthcare application, right? The existing method, right, to analyze the performance are all based on accuracy, or as well as some other kinds of matrix, right? But for some application like the healthcare, right? So for example, given 100 testing sample and 99 of them are correct, yeah, but one is wrong, right? So the accuracy could be 99%. But this one misclassified sample can lead to severe consequence, right? So how can we analyze these cases, right? And how can we explore more corner cases, right? Which is beyond the neuron coverage. Okay, so I think that's all about it. Thank you very much.
Great. Thank you very much, Haoliang. That was a very, very interesting talk. Do we have any questions from the floor or online? Yes, Fayaz, go ahead.
Very nice talk. I really like the idea of neural coverage, but I was thinking that perhaps a similar effect could be achieved by just using dropout. And I was wondering if you would compare to that. That also maximizes neural coverage.
Sorry, I cannot hear you clearly.
So I think if I understand the question correctly, the question is, did you compare with dropout? Because dropout might have similar kind of effect. Is that right?
Oh, yes. Actually, in the model, we have the dropout layer. Yeah, like that. And also dropout, actually, there is no contradict between the dropout as well as our neuron coverage. Because the idea of neuron coverage is that as long as the neuron has been activated by at least one single input, so we can think of this this neuron has been activated like that. We do not consider to say that the neuron has to be activated by all inputs. No, it's not like that. Yeah, just one single input. So we say, so there is no contradiction between our proposed coverage as well as dropout.
Okay, I have a very quick question, if I may. So the idea of neuron coverage, how important is it to make sure that you have as much coverage as possible?
Yes. Actually, I think the coverage actually give us a new direction to analyze the generalization capability of our neural networks. So one possible, right? So how this coverage can be applied is that nowadays, how do we analyze the generalization capability, right? Is for example, many benchmark data set right? So we have A, B, C for training, and we test on D, right? As long as we have a very good performance on D, and then maybe we can claim that the model can be generalized. But what if E, F, and G, right? So we have many unknown data sets in practice. So I think one good thing for neural coverage is that, maybe this can shed light on how we can analyze the generalization capability of a neural net without the testing samples, like that. So as you can see, based on our method, right? So our method actually does not rely on the testing sample, right? So maybe one possible direction is that whether we can use this matrix, this term, right? Maybe as a matrix, right? To analyze if our model can be generalized well or not. But we do some analysis. Unfortunately, we do not find some such trend. One possible reason is that the coverage, the neural coverage we are using for this research work is still quite toy, right? So we still have a pretty fine threshold, like that. So how do we define a more proper neural coverage? So actually, there are a lot of people in the community of software engineering, security, people there explore in this direction. So I think in the future, it's quite interesting to see, whether we can marry the advantage of AI and engineering, right, to see what happens.
Thank you very much for a great talk again.
Thank you.